Since an action potential brings the membrane potential past threshold in a segment of the membrane, it can stimulate the opening of voltage-gated ion channels that are close enough to its depolarization. This means one action potential can cause another action potential. In these cases, sodium and potassium channels open and close just as they did at the trigger zone, and a new action potential is produced. This one also excites the membrane and opens nearby voltage-gated ion channels. And so does that one. And so on, all the way down to the end of the axon. Just like falling dominoes, tip the first one, and the rest fall in order, all the way to the final domino. Since already depolarized or hyperpolarized membranes cannot be stimulated, action potentials can't go backwards and trigger proximal regions of the axon. The wave of action potentials is called a nerve signal, and it's an electrical current that doesn't lose strength, but it is also much slower than one through a wire. In an unmyelinated axon, every single segment of the membrane has to depolarize. This is a slow process called continuous conduction. But in a myelinated axon, there is no depolarization at the myelin-covered internodes. When the node of Ranvier depolarizes, sodium ions rushing in will electrically repel other sodium ions that are already in the axon, pushing them toward the next node of Ranvier. These ions stimulate an action potential in the next node, and this also continues until the end of the axon. We call this saltatory conduction, and since only the nodes have to depolarize, it is much faster than continuous conduction.